Hi all, welcome to the next session of Embedded Software Testing Unit 2 series. This is lecture 21. So today we study more about the white box testing techniques and continue our white box testing understanding with more details. And we'll try to conclude this Unit 2 in today's session, if not in the next session. And in yesterday's session, we discussed about Um, the other techniques of white box testing such as branch condition testing, and before that we studied statement testing, branch condition testing, data flow testing. So in branch condition we know that the testing does source code which finds out decisions and the individual boolean operands, and the boolean operands within the decision conditions will be tested with the help of decision condition testing, or this also called as branch condition testing. The next type of testing which is also called in terms of aerospace industry MCDC, branch condition combination testing, where the testing aspects will be done on the source code which recognizes the decisions and the individual boolean operands within the decision conditions. All the possible values that are going to be fed into the boolean operands within the decisions will be tested. So accordingly, test cases will be designed such a way that independency is achieved. Then we have studied about modified condition testing, where the outcomes, especially the result, whatever it is going to arrive at, will be tested. Also, the last one, the linear code or sequence and jump testing we did. Here we have seen three types of TER test effectiveness ratios, where TER1 is the number of statements, statement coverage basically. TER2 is number of control flow branches versus control flow total branches. The last one is LCSEJ is executed. So they used to use it initially, but nowadays they use the other type of testing. So we also went through some of the examples, and there is a LCSEJ table and the total number of LCSEJ numbers with the start line, finish line, and the jump line will be addressed. The last one is the D1 Senate specific testing is called MCDC. Basically, D1 Senate life cycle has processes addressing to each life cycle activities such as planning, development, and testing. Testing is called as integral process, and under development, it has requirements, design, coding, and integration. And we have studied about a few examples of the AND gates, the OR gates, how a truth table can be arrived. So this type of testing is also called as a truth table approach, where all the possible combinations which yields the independency as well as the outcome of the testing will be tabled, and accordingly the tests will be driven. Okay. So in today's session we will study about gray box testing. As I said in one of the class, it is a mix of both white box as well as black box. Sometimes what will happen is the black box may not be sufficient to support the coverage or the justification in terms of testing. Similarly, the black box also may not be enough. So we need to balance between both of them, especially the integration test cases and the system, some of the system test cases and some of the white box coverage. We need to be balanced. So with the type of gray box testing that is addressed, white box test can be intimately connected to the internals of the code. They can be more expensive to maintain than black box test because of the complexity and other factors. Tests that only know a little about the internals are sometimes called as gray box tests. Here what I said is some knowledge of the internals will be known. Gray box test can be very effective when coupled with error guessing. So another type of method called error guessing, where the errors are guessed based on the knowledge of the unit under test, and that will be implemented. The test design will be applied accordingly. So these tests are gray box because they cover specific portions of the code. They are error guessing because they are chosen based on the guess about what errors are likely. That means the test will be carried out as a pre-test sort of a thing. Then the user has a knowledge about what could be the likely failures that could come, and based on his knowledge uh, about the system and about the code, so he will balance between a specific portion of the code as well as the black box features. So he will apply certain test cases. Those test mechanism is called gray box testing. So this testing strategy is useful when you are integrating new functionality with a stable base of legacy code. So that means that we have a base code which is working most of the time, and which doesn't have much issues or which doesn't have unknown issues, and there is a new piece of code or functionality is being added. So what we do is we'll try to understand how the functionality is being implemented with the help of a piece of code, and with the help of a system understanding of the knowledge, we'll try to apply new test cases. So this kind of new test cases mechanism is called as gray box testing. Okay. The next one, these are all basically uh, the additional details what I am trying to give in terms of white box testing. The main methods in white box testing in terms of coverage and all we have covered in earlier. We will add to that. There are different testing methods and the testing philosophy and the test details that needs to be studied. Okay. So we will study about a test driver and a test stub. So what is a test driver? What is a test stub? You might have heard about this. So all the embedded systems having embedded system testing mechanism will apply this test driver and test stub. It's particularly useful for software testing where unit testing is done. So okay, a test driver. So software which executes software in order to test it. That means test driver is again a piece of software. It's a test software which executes what the software, that is embedded software unit which is under test to test it. So providing a framework for setting input parameters, executing the unit and reading the output parameters. I have a diagram in the next slide. I will explain. You can understand better. So what will happen is sometimes some of the input parameters, execution and expected output may not be possible with a realistic inputs. So what we need to have is development of a small driver which drives all these inputs, and it calls the piece of software under the test and expects the result. So with the help of test driver, this will be done. A test stub, imitation of an unit used in place of the real unit to facilitate testing. So this is a complement basically of the test driver on the other side, where the actual piece of software which is supposed to work will be replaced with a stub, so that we know that test driver is working or not properly, to see that what is expected, and the same thing will be replaced with the actual piece of software to compare the expected result and arrive at the conclusion that the tests have been passed or failed. So that is how a test stub is used. You go to this diagram. This will give a clear picture of how the test driver and the test stub is used. So basically, the book refers to this diagram. Of course, test bed is a test setup or environment having both the driver on the one side and stub on the other side, and the unit is used in the middle. You can see the driver calls unit under test, and the unit under test can be replaced with the help of stub. is like a wrapper we can have for this. So what does this wrapper do? Basically, uh, whatever the information that we need to get it from this unit will be driven from this driver, and wherever the possible expected output that is expected from this unit will be done with the help of the stub. So stub is going to be replace the actual unit, which is unit under test. So that is the basic of test stub and drivers. So interfaces between two system parts can how why it is used. Basically, test stub and test drivers are basically for the interfaces. So two system parts in order to test the interface. So on the one side we use the driver because the other side we are going to have an interface, and when they are closely in conjunction we may not be able to test it. So for example, so we have a UUT1, and suppose we have a UUT2, and we want to test UUT1 with parameters such as parameter 1, parameter 2, and expected output as expected output 1, expected output suppose. And how does this UUT1 is going to get the data is with the help of UUT2. So what will happen is there is a interaction between these, and what we are going to do is we are going to replace this piece with the help of test driver, and similarly vice versa. While testing this piece of interface with the parameters, we are going to use a test driver here. Maybe one we can call here, in this case it is 4. So likewise, the interfaces between two system parts can be tested with the help of this mechanism if both systems are available. Here available means available for the uh, tester to test it independently. So that's what it means. Or if it is not available, then we are going to club both of them and drive it at a higher level. So this can have consequences for the testing time, because the time is more required for us actually. To avoid this and to start testing the system part as early as possible, stubs and drivers are used. That means still suppose some functionality in the embedded system is completely developed and other functionality is not being developed. How we are going to test that implemented or ready functionalities with the help of drivers, where specification details are known, and with the help of inputs and the parameters, the test drivers are developed and tested. So basically, it is useful for testing the interfaces. So a stub is called by the system under test and provides the information the missing system part should have been given, and a driver calls the system part. Standardization and use of a test bed architecture. Uh, Basically, if you have this test bed architecture defined in the early stage of the project, it will be very good for each piece of the software unit under test. So it will greatly improve the effective use of stubs and drivers. The test bed provides a standard interface for both the tester to construct and execute test cases, and for the stubs. So each separate unit to be tested must have a stub. So we need to have a stub as well as a driver to test both of them interchangeably. And techniques for test automation such as data-driven testing can be applied effectively here where data is very important, and all the type of data what we have studied in earlier session like P case, C case, CUs and all that can be tested with the help of this, where the combinations of inputs that needs to be driven can be done with this actually. So such a test bed architecture facilitates the testing of any unit. The reuse of such tests during integration testing and large scale automation of low level testing is easier basically. So considering all these aspects, so we need to have test hubs and drivers. Okay, so that is about test hubs and drivers and gray box testing uh, with the white box testing mechanism. Now we will come to the various coverage testing tools that are used in the industry in general. So logic analyzer, software performance analyzer, timing analyzer, vector cast, LDRA, RTRT. There are a lot of tools like this, so which will help, which will basically used for having the coverage and the instrumentation, the unit testing, etc. will be done with the help of this. It could be one tool or multiple tools depending on the complexity of the embedded software that is being used. Okay, let us try to study or understand the basic thing about these tools. Okay, vector cast. This is a tool from Vector Cast Corporation. In aerospace, this is being used more, where they define different levels and they do the instrumentation of the source code and they run that tool, and we will get the report such as this, what is being shown below. So for a database sort of a application in aerospace, this is being used. You can see the metrics, what are the metrics it generates. So with the help of this metrics, the conclusion will be done so as to see that whether the vector cast tested output is 100% coverage done or not done. You can see there is a database, total 5 number of database have been tested here, and the complexity is 5 straightforward testing, and the unit be level A state is 100%. That means all the statements or the decisions or the conditions that are there for each of these, there are about 10 out of 10 have been executed, saying that the coverage is 100%. Similarly, you see another piece of software that is being tested with the help of VectorCast, some functionality or a package called Manager. And this has 1, 2, 3, 4, 5 types of sub functionality like place order, clear table, get check total, etc. Each of them have been tested with the help of VectorCast with the instrumentation mechanism, and you can see the complexity. It has a complexity of 5. We'll try to understand what is complexity in the next unit, I guess, unit 3. And complexity of other pieces is 1, here it is 3, last one is 2. So there are total 12 complexity measures that have been tested here with the help of VectorCast. And the coverage is something like 63% in the first, where the place order is being executed, and coverage is 14 out of 22. That means to say that the complexity, the coverage needs to be done for 22 executable statements or decisions or whatever it is, but out of which only 14 of it have been covered, saying that 63% have been covered. Similarly, for the next, you can see 100% coverage, and this one is 77%, 7 out of 9, and the last one is 0%, saying that none of the statements have been executed or have been invoked with the help of this tool, whatever the instrumentation we have done. So altogether they generate the metrics. Of course, we study about test metrics and all that in separate session in detail, but to have a glance of what tools commercially they are using it, I'm just trying to present it the various tools. The overall coverage is 71%, and the right hand side the one more column that is for a different piece of functionality or things that will be showcased. The next one is LDRA. It is from LDRA, and it is also one of the popular tool that is being used in the aerospace industry. Here also similar to what instrumentation we have seen. So the reports can be generated, which will help in terms of doing the in testing. We can see how many test cases have been used, what of them are passed. So what is the report, and likewise we have a complete coverage of the unit under test. Okay. So the next one is being RTRT. This is also one of the good competitor and a popular tool that is being used in different industries, including application, finance, embedded automotive, telecom, aerospace, etc. Widely it is used, but they have a different variants of this tool, such as RTRT bed, RTRT embed, likewise. So it is from IBM. You can see the details in that website or their website. There's a data sheet and all that, which talks about this. So the rational test real time is called as RTRT. So what it does is the source code such as C, C++, ADA, whatever it is fed into that RTRT tool. So what it does is the below steps are there part of the RTRT in terms of configuring and using it. So the environment will be defined first. The test harness will be created, and with the help of test harness, stubs will be generated. Then we will have executables for the corresponding test harness. Then actually we execute the test. After execution of the test on the target environment, we have the results, and the results will be used to report it. What is the coverage and all? You can see on the right hand side. This is the code coverage, performance, memory, trace analysis, all these aspects of the testing, white box testing will be done. And similarly, test results will be reported to support this coverage or justify the coverage to analyze it. And it uses the cross compiler such as GNU, GCC, etc. to compile the developed test harness and the builds. And it uses the target such as microcontrollers. It could be having the RTOS, or it could be with a host machine simulators or emulators on the target machine. So that is how the RTRT is been structured to use on the white box testing methods. Okay, so that is what is about the commercial tools used for white box. So let us try to study what is a logic analyzer. Basically, logic analyzer can record memory access activity in real time. It is a potential tool for measuring test coverage. So what it does is we have various test hooks within the embedded system, and the test hooks will record different data in a dedicated piece of memory, and that memory can be recorded with the help of this analyzer. That analyzer is called logic analyzer, and there are logic analyzer probes that will be hooked into the memory, and with the help of probes it will acquire the data in real time and will have the coverage and will provide the coverage results and reports. A logic analyzer is designed to be used in trigger and capture mode. That means the logic analyzer can be used as triggering and capturing mode for the memory or the interfaces that is being hooked for that piece of. It's basically hardware and software both that logic analyzer has. I may not have a diagram here. Maybe in future class I'll try to show how it looks. The logic analyzer is. Uh, the logic analyzer is designed to be used in the trigger and capture mode. It's difficult to convert its trace data into coverage data. So what it means is the trace data, whatever we got it, we may not be able to cover it. We may not be able to convert that into coverage with the help of this. But what it does is the overall measurement it does. We do a sampling method that's called statistical sampling. So with the help of this, logic analyzer can be used to have a coverage on the trace data on the triggered mechanism. Okay. In continuation of the logic analyzer, in particular, it's difficult for sampling methods to give a good picture of ISR test, especially the piece of software having ISR. ISR is nothing but interrupt service routine. You must be aware of this. So basically, this is the part and parcel of the embedded software where an interrupt occurs for the normal flow. That interrupt has to be handled with a piece of control flow or functional flow or whatever the action that is needed. That action and all will be part of the routine called interrupt service routine. A good ISR is fast, meaning to say that ISR has to be short and sweet. It needs to get fast and come out of that routine. That means it needs to do certain flag settings or certain minimum actions so that it can come out very fast. ISR cannot be bigger, it cannot be complex, and it cannot afford to take more time. If an ISR is infrequent, that means the frequency of the ISR happening in the embedded life cycle is less. The probability of capturing it during any particular trace event is correspondingly low. That means capturing the trace data is lower because ISR is happening very less frequency. That's easy to set the logic analyzer to trigger on ISR axis. So, but easy to set the logic analyzer because the capturing mechanism will be easier. Thus, coverage of ISR and other low frequency code can be measured by making a separate run through the test suite with the logic analyzer set to trigger and trace just that code. So, what can happen is we are trying to focus only the piece of software which are part of the ISR. So, what we can do, since ISRs are very fast and very frequently happening within the system, and the system having complexity in terms of more number of ISRs, what best can be done with the logic analyzer is that we can comment out the rest of the code and focus only on the ISR, what is, and trigger that and capture the data what ISR is supposed to do and analyze the captured data with the help of logic analyzer and do the coverage whether ISR is capable of doing or covering all the intended result. Okay. So there is another set of tool. It is called software performance analyzer. So performance could be in terms of memory. Performance could be in terms of memory. That means memory has to be accurate or intended for certain portion of it. Suppose, say, a requirement could say 50% of buffer memory to be reserved for future upgrade or scalability, etc. So what will happen is, meaning to say that, for example, if you have a 1 MB of memory, we should have 512 KB of memory as reserved against 1 MB. So that is a requirement. And how do we test how much the software is taking? So there are a lot of methods and there are a lot of tools also. So those are all coming under performance analyzer. By using the information from the link of roadmap, these tools can display coverage information on a function or module basis rather than raw memory approaches. So this is a map file for each of the embedded project. This will be done with the help of build. This compile plus link. With the help of this, the map file will be generated. This map file will have all the information such as the addresses, the opcodes, and the BSS stack and all the information. With the help of that memory map, we know that how much it is going to take this build for that particular embedded project. With the help of that, we should be able to arrive at the performance of that particular unit. So for that, there are tools, analyzers from different vendors, but mostly it will be done manually or statically basically. Okay, so performance testing and consequently performance tuning are not only important as part of your functional testing, but also as part of important tools for the maintenance and upgrade phase of the embedded lifecycle. So another important aspect of performance is memory, we know, speed, speed with load, they say. So it's very important to have the performance of the embedded system stable and continuous without the change and with efficiency, having scalability and modularity. This is one of the performance requirement. They use it. Not only it is enough to have a memory satisfied. Speed speed means not fast basically. With various conditions on the field, you should be able to perform consistently and scalably, etc. The other thing is timing. It should be accurate and stable. So this is also one of the performance measure. They have it. So performance testing and consequently performance tuning are not only important as part of your functional testing, but also as important tools for the maintenance and upgrade. Upgradability is more because embedded system is ever living and growing because of the fixes in the requirements and more requirements getting added in the embedded lifecycle. Performance testing is crucial for embedded system design and unfortunately is usually the one type of software characterization test that is most often ignored. That means I've seen many of the embedded system world industries, they give less priority to performance testing and tuning, especially in the beginning or the middle of the project, but they struggle in the end because they would not have met the criteria of performance, and a lot of bugs and errors will occur due to the performance issues. That is why it's very important to have an understanding of what is the performance of the embedded system. Accordingly, we need to have testing mechanism, especially on the memory, speed, timing, and the load of the unit. And we should use the analyzers such as performance analyzers and map files and all that. Probably we'll try to touch base simple map file to have an understanding of what it does. But basically, it is part of the embedded system course. I'll try to just address it in the future class. Okay. The next one is, as I said, memory usage. What sort of a memory usage is there in the embedded system? So basically, we use a memory map. With the help of memory map, we will be able to analyze the stack, the inbuilt memory. It could be the RAM, ROM is it could be a flash, or we can have a small footprint in terms of faults and all that. Usually that will be stored in NVM. It's also called as EEPROM, electrically erasable or programmable read-only memory. So there are various types of tests. For example, for EEPROM they use the pattern test, and for flash they use the integrity test. Integrity test can be done with the help of working ones, where each memory cell is tested with zeros and ones. That means whether each cell is capable of flashing or programming a 0, a programming 1. So that is also called as a pattern test. Usually they use, if it is 16-bit, 5A, 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 5A. You can see why 5A it is, because 5A is nothing but, I'll write it down in binary. 1 is 5, 0, 1, 0, 1. Whereas A is 1, 0, 1, 0. Is 10. So we know that the cells, the first cell is addressed here this with 0, and the same is cell is addressed with 1. Similarly, the next cell is addressed with 1, and then next the same cell is filled with 0. So likewise, we are going to have a pattern test or walking one test where each cell in the memory will be tested. So on the memory, like flash or RAM, the same testing is done. So mostly these tests are basically built along with the code, because there are requirements which talks about these tests have to be there frequently, should be done in the embedded systems. So they will have an implementation in the embedded system itself at certain frequency when the system is running. But we need to log whether that there are any failures for such tests. These tests are called built-in tests. Built-in tests. There are different types of built-in tests. That is not scope of this, depending on the embedded systems that we use, and all this will be logged with the help of those tests. So that is part of the memory usage and memory testing they do in the embedded software testing. Okay, the next one is the timing analysis. So there are stringent timing requirements to test and analyze the timing, how much the embedded system is taking. Timing analysis have to be conducted. And mostly the timing analysis are done with the help of the time machines and trace machines which are available in the debugger itself. The IDE is nothing but integrated development environment, such as multi, Lauterbach, Code Warrior, etc. All these debuggers have inbuilt time machines or trace machines, and that will be used. That is helpful in finding the timing requirements in terms of unlocking code and putting the breakpoint and uh, measure the time, how much it is taking and all this stuff. So we can validate with the help of that. Some of the embedded systems will provide ports, and that port, which as LEDs, you can say, can be inspected, or IO ports. So which will toggle for certain range or certain frequency, and that can be put into the scope. Scope means oscilloscope. We have multi-channel oscilloscope from Agilent, Trident, etc. So we can use any of that oscilloscopes to measure it. So such embedded systems will have to have ports available, but it may so happen that the ports may not be there because it's additional hardware, and they may not be able to they cannot, or they may not be able to afford to have that because it is going to occupy a space and more current, etc. For intermediate testing before the last build, they may be having it within the part of the board or the target board or the FPGA, whatever it is. With the help of that, the timing can be tested where the embedded software will be triggering upon certain events, and that events can be captured in the oscilloscope. And for ISRs, we can analyze through IDE, where ISRs we can have a counter and how much the counter is getting updated. The counter also can have registers. The timing registers can be used along with the counters to arrive at how much time it has taken. So manually this will be done to analyze the ISR timings, etc. Then we have inbuilt registers on the target systems and microcontrollers such as watchdog and all stuff. With the help of those we can test it. Watchdog registers, timing registers, RTCs, RTC is nothing but real-time clock. All this can be used for doing the timing analysis. So with the help of this, we can do the timing analysis. Okay, so having understood the various tools and all that, the applicability we need to understand for the life cycle. Coming to the testing tools, so there is a life cycle that is being categorized. So we'll try to understand in brief what is this tools life cycle. Basically, it is called the various tools, how they are getting used, how they are getting categorized. So what is the use and all that. Quickly, we'll try to understand based on whatever the type of tools that we need to have in the embedded software testing. Okay, so you can see a diagram here that depicts about the various tools related to the testing life cycle. So we know that there are as per the TM method or the LITO principles what we have studied, there is a life cycle PSEC, the preparation, execution and all the stuff, completion and all that stuff. So we have various tools for P preparation. We have a case tool analyzer, complexity analyzer. For specification, we have test case generation or test case generator that will help in developing the test cases. And for execution, we have test data generator, record and playback tool, load and stress tool, simulator, debugger, etc. There are a number of tools. Doesn't mean that all need to be used, but it's a categorization basically that need to be applied and planned. These are all be part of the planning, software verification planning, which we have studied in our earlier sessions. Similarly, for completion, we have a reporting mechanism and all that. And overall, for P&C planning and control, we have different tools in terms of defect management, test management, configuration management, scheduling and progress monitoring tool. Okay, so this is how the life cycle data or the life cycle aspects of the testing will be considered in terms of categorizing the testing tools. And we'll try to study some of them in detail as we go through some of the sessions like defect management or test management, configuration management in the future classes. Okay, so that is about the life cycle. We'll try to quickly understand each tool such as planning and control. There is a defect management tool. A defect management system is used to store defects, trace them and generate the progress and status reports. Defects detected during the test process must be collected in an orderly way. It should be organized properly. For a small project, a simple file system with a few control procedures is sufficient, whereas the more complex projects need to have at least a database sort of a thing with the possibility of generating progress reports. The tool should help basically. This will help the testing team to analyze where they are. So defect management tools such as Bugzilla can be used for management of the defects. So that is part of the planning and control. The next one is a test management tool. So the tools with the ability to link system requirements to test cases. Basically, how the tests are managed, how they can be traced. All this will be part of this. So the tool should have the ability to link the requirements into the test cases. They become very useful if system requirements are changed or might change. Why this we need all these tools is it's very important to have control of the changes. So how do we do? So with the help of these tools. So it's very easy to change it, to plug the new requirements or deletion of the requirement, etc. So all this can be done with the help of test management tool. Then we have a scheduling and progress monitoring tool. There are a number of tools available for scheduling and progress monitoring, such as the MPP and all. You have seen there are different tools also which can be integrated along with the test management tools such as TestLink or Bugzilla for defect management, etc. So it's very easy with the help of these tools for scheduling and progress monitoring. Very useful for a test manager combined with information from the defect and test management systems. And preparation phase and specification phase tools. On the left hand side you can see is the preparation phase and specification phase. There are case tool analyzer, complexity analyzer, test case generator. We'll try to understand what are those. Probably we'll try to detail it out in the future sessions. Okay. Case tool generator preparation phase, they use it especially for those where we use object oriented sort of embedded systems or model based systems. The tools such as UML based tools are used for consistency checks and all that. So they'll be able to help in terms of the preparation phase. So they can be used to check whether or not the design has omitted any things or any consistency between different design elements, etc. So this is basically testability review of the test basis, what way is getting planned in terms of preparation. So the next one is a complexity analyzer. We try to study the complexity, software complexity in the future class. Basically, this complexity analyzer, such as understand for C++ from Sky Tools, is capable of giving indication about the complexity of the software. The degree of complexity is an indicator of the chance of errors occurring and also the number of test cases, how much we need and all to test the system thoroughly. So for this, they use a standard called McCabe complexity. This is one of the important or good complexity measure generally they follow in the industry, which identifies the complexity. This is basically getting identified. I can explain that in one of the next class with the formula and all that. We need to know about edge and nodes. Basically, we know that embedded software can have multiple edges and nodes based on the decisions and the flow of the software. With the help of that, the complexity is arrived. Okay. The next one is the test case generator. This is for the specification, test specification or test cases. So there are test case generators such as MATLAB, LabVIEWs, and all that. But sorry, LabVIEWs and all are used as a script and all this stuff. So using something like Excel sheet based tools or BC or Python even or Perl, these can be used from inputs such as requirements to test cases. So with the help of this tool, the test cases can be generated automatically and consistently. It will be used for different requirements, changing requirements and all that. So that's how test case generators are used in the preparation and specification phase of the embedded system testing. So next one we have is the execution. The execution can be done with number of tools and the various types of things that we have. Definitely minimum 3 to 4 tools to be used for any of the embedded systems having a moderate complexity. And here is a list of the type of tools that are used in the execution phase. Test data generators, record and playback tool, load and stress test, simulators. We know we have studied about some simulators, stubs and drivers. We studied this today. Debuggers. We know that IDEs are used as debuggers for code analysis and all that. We have a static source code analyzer, such as understand for C++, ECLint, likewise, and poverty is also another code analyzer. Error detection tool in the code, performance analyzers, memory analyzers, then we have code coverage analyzers such as the instrumentation analyzers, vectorcast, RTLT, and LDRA, likewise. So we have a thread and event analyzer where we use in RTOS, which is living with the multiple threads and all that. Then other one is called threat detection tool. It's a specific tool where if there is a threat to the embedded software system due to erroneous code or a dangerous way of having the crash, etc., that can be identified with the help of this mechanism with this tool. So that is how the execution phase. The tools are categorized. So having understood these testing tools and all that, we will try to understand testing terminology and all that stuff in the next class. There is a configuration management tool also used. We'll try to go through that in the next class.